Good morning, good afternoon, or good evening, whichever is appropriate. This is lecture number 16, and I have the feeling that it's going to be a relatively short lecture for a reason that I will tell you at the end of this lecture. Okay, you remember that in the last lecture, we derived the Lorentz transmission law, transformations, which tells you the coordinate and the time of an event in terms of in a frame, in terms of the locations and time of that event in another frame. Let's say that we have two frames, S frame and prime frame, and S prime frame, S prime frame, the primed frame. And for me, and for this class, for this, S prime is defined to be a frame moving relative to the S frame towards the right hand side, towards positive x-axis. X-axis and x prime axis are understood to be collinear. I cannot draw them on top of each other, otherwise you cannot see. And last time we showed that the time and location in the prime frame is related to those in the prime frame in this given by these four equations. And the y and z coordinates just come for right, since we assume that the relative motions along the x direction. All right, last and this is assuming that in fact the origins of the two frames coincide at time 0. All right, and then we reverse this is the prime in terms of unprimed, and here I've written down the unprimed in terms of the primed. The delta here stands for the difference of two events. This one stands for x1 minus x2, etc. And if those two events are very close by, I may even use notation dx, dt, etc., which I will do later on at a certain point in this lecture. And also last time we derived the rule for the transformation of velocities. Namely that if an object travels with velocity u prime, or in fact this refers to just the x coordinate. And we also derived similar expressions for the component, the y and z components of the velocities last time. But let's concentrate on the x component of the velocity. Let's say that the object moves only along the x direction. Then, the velocity of that object in the unprimed frame, which we call u, is given in terms of the velocity of that object in the prime frame. This is the expression. So of course, if the velocities of the object we're talking about moves, if the object moves relatively slow compared to the speed of light, and if these two coordinate systems move relative to each other with a relatively small speed compared to the speed of light, then of course we can omit this term in the denominator. Then u will be just u prime plus v. This of course is the familiar law of the additional law of relativity in Galileo transformation for the non-relativity case. But the very fact that there is such a term in the denominator means that in fact the additional law no longer applies. So this lack of addition of velocities gives us this term. Turns out, well, we showed that in fact it was crucial to have that lack of addition of velocities. The reason that is that this term is very important when we talk about velocities of objects moving with velocity comparable with speed of light. In particular, which if the object happens to be just a beam of light, then we showed last time that this term is very crucial in ensuring that light travels with speed of light c in one frame, travels with the same speed, c, in another frame. Okay, and this, of course, is important. It's important check. Okay, of what we have done is consistent with the second postulate of special relativity. Okay, light travels with the same speed in all frames, independent of directions, etc. All right. Now, so as I said, this expression shows the lack of additional velocities. But we wonder if there's another measure of velocity in terms of which we can rewrite this in such a way that the addition law of that velocity parameter applies. And it turns out to be yes, as I'll show you. And I'm going to show you that if I write u prime and v u prime and v in terms of hyperbolic functions. I'm going to remind you what hyperbolic functions are in a moment. Okay. Let's define this to be tangent, hyperbolic tangent function of a parameter called theta. And this one, hyperbolic function of an angle, theta prime. V, well, since V stands for the velocities between these two frames. So this is velocity of prime frame relative to the S frame. So let me attach subscript R with this angle. Then in terms, oh, sorry. Okay. Actually, U prime and V, of course, have dimensions of velocity. So this is dimensionless, so I better divide it by c, speed of light. And in fact, at this point, let me also call this beta, and this we call beta prime, and this we call beta sub r. So write u over c, u prime over c, v over c in terms of the hyperbolic functions of these angles. Then I'll show you that. This can be written as theta equals to theta prime plus theta sub r. So obviously, there's no denominator on the right side. So this is a certain kind of measure of velocity. And sometimes I think this are known as rapidity. It tells you how rapid things travel. In terms of these rapidity parameters, the additional laws of velocity does seem to apply. All right. Now that I've introduced the hyperbolic function, let me remind you what they are. And to do that, let me in fact use some. Oh well, let's see. May as well do it here. Let me remind you that review. Let me remind you that sine of theta can be written as e to the I theta minus e to the minus I theta divided by 2I. Cosine theta is equal to e to the I theta plus e to the minus I theta divided by 2. And of course, okay, tangent theta is just the ratio of sine theta and cosine theta. So these are trigonometric functions, the sine, cosine, and tangent. Now, okay, in case you're not familiar with hyperbolic functions, hyperbolic functions can be written in a similar manner. Namely that hyperbolic sine function. Sometimes I just pronounce it as sinh. Sinh, yeah, it should be sinh. But hyperbolic sine function, okay, theta is defined to be e to the theta minus e to the minus theta divided by 2. And cos hyperbolic cosine function is defined to be e to the theta plus e to the minus theta divided by 2. And hyperbolic tangent, tangent is defined to be hyperbolic function, sine function divided by cosine, hyperbolic cosine theta. And then, with this side by side, you can check right away that sine of I theta is I hyperbolic function. And cosine I theta is equal to cos theta. And accordingly, tangent of an imaginary angle, I theta, is I tangent theta. You can check very clearly. Okay, let me just check one for you. Okay, sine of I theta is equal to E, replace theta by I theta, then I minus theta minus e to the this opposite side, so plus theta, divided by 2I. So that I can interchange these two and put I upstairs. So this will be I e to the plus theta minus e to the minus theta divided by 2. Lo and behold, this is nothing but the hyperbolic sine function. So this is I hyperbolic sine function. Hence, first identity. Okay, let me write down a few useful identities involving hyperbolic functions. Obviously, now cosine. I'll keep this on the board. So let me look at cosine theta. Okay. Should I introduce it at this point or otherwise? Okay. Yes, I think it might be better this way. Okay, yeah. Cosine theta, you remember, is equal 1 over square root of 1. The important thing is that this is plus tangent square theta. And that, in that case, sine of theta would be equal to, that's equal to tangent of theta, which is sine of times cosine theta, isn't it? Cosine theta. Let me see. Tangent is sine over cosine, correct? And this is equal to tangent theta divided by square root of 1 plus tangent square theta. All right? Also, we know that the cosine square theta plus sine square theta is 1. Let's now, in fact, replace those angles by the imaginary angle. So that if I can consider cosine of I theta, that will be equal to 1 over square root of 1 plus tangent square of I theta. Run out of space. But what's this? This is hyperbolic cosine theta. And this one is tangent. I theta is I tangents. And this square, so this become 1 over square root of 1. Notice, minus sign instead of plus sign here. Tangent square theta. And the sine theta, so if I have now I can do the same thing for this. Then we'll find out that hyperbolic sine function is equal to tangent theta times cos theta. All right, and then find this one. No, not find it. There's one more to go. Cosine square plus sine square. So if I talk about cosine square, square of cosine I theta. Cosine I theta is cos. So I have cos square of cos theta. Square of sine I theta. Sine of I theta is I. Hyperbolic sine function is, if I square it, then I square will be minus 1. So minus this square is 1. So that's crucial to difference in sign. Minus, there's a plus here. And this plus here versus this minus. One more. Then we can go back to do physics. Yeah, we know that tangent of the sum of two angles, let's say called alpha plus beta, you remember, is equal to tangent of theta plus tangent of beta divided by 1, minus tangent theta tangent beta. The sign of this is crucial. And now I consider, I theta goes to I theta, beta goes to the I beta, then you will get on the left hand side, you will get, there's an I, but that will cancel the I on the right hand side. So you will get tangent of theta plus beta is equal to tangent theta plus tangent beta over 1, instead of minus, we have plus. We are sharp. Plus. Instead of minus, we have plus. Of tangent theta tangent beta. So, okay, with the help of this table, okay, now, okay, it is, okay, you can work with hyperbolic functions easily. All right, so let me show that this additional law can be written in terms of this. If these angles are related to u prime v in terms of hyperbolic functions of these angles. And let me show you that is true. Okay. So to do that, let me rewrite this. Divide by c. Divide by c. Here. Divide by c. And let me write this as u prime over c times v over c. U over c, oh, did I? Yeah, oh, so sorry. I hope now you can see it a bit. U over c is beta. So this becomes beta is equal to beta prime plus beta sub r over 1. The crucial thing is that this is plus and not minus, as we will see in a moment. Plus beta prime times beta r. The lack of addition of velocities as given by this now appears as the fact that beta is not just the sum of beta prime and beta sub r, but there's this denominator. But I'm going to claim that in fact, in terms of the angles, theta prime and theta r, defined here. So hyperbolic function of theta is beta, etc. Then, in fact, this complicated looking additional laws of the velocity is in fact can be shown to be this. All right, let me show that. To do that, all I have to do is that let me consider tangent of theta. That of course is beta. And this is equal to tangent of theta prime and theta sub r. But now, I can apply this identity for the tangent of the sum of two, so that I will have, in that case, this is equal to, making use of this identity. So, here, this is equal to tangent theta prime plus tangent of theta r divided by 1 plus tangent theta, of course, is, so tangent theta prime times tangent theta r. But tangent theta is, as I said, beta. And what is this? Tangent theta prime is beta prime. Tangent theta r is beta sub r. Then 1 plus tangent theta prime is, beta prime. And tangent theta sub r is beta sub r. So that we get, if theta is equal to theta prime plus theta r, and the thetas are defined, in such a way as to be equal to those betas. Okay. Then, lo and behold, okay, we have this additional law of velocity back. Beta is equal to beta prime plus beta sub r divided by 1 plus beta 1. Okay, so this is correct if we are willing to introduce the hyperbolic functions. And as I said, these parameters are known as velocity. It's sometimes known as, well, I call them velocity parameters, some kind of parameters in terms of which we can write down the additional laws of velocity very simply. Okay. But okay, in the literature, sometimes I think they are called parameter rapidity. Rapidity. It's a measure of how rapid things go. Okay. And you may think that, well, you have been wasting my time in introducing those angles. But it turns out that sometimes it's a nice, well, it brings out some nice features, as I'll try to demonstrate in a moment. All right? And at this point, let me also take the opportunity to introduce, so beta introduce, I have beta sub r. Let me see. So beta, let me write this down here. Maybe I should use different color. Oh, beta sub r is defined to be V over C. And since there's 1 over square root of 1 minus V squared C squared appears often, so let me in fact give that a name. So that also I will introduce gamma, which is defined to be 1 over square root of 1 minus beta sub r squared. Okay, so this of course is 1 over square root of 1 minus v squared over c squared. So this is gamma. Okay. So I will introduce beta sub r as v of c, and gamma is this complicated thing. And after a while, I will drop the subscript r. The reason being that, in fact, we have to introduce r here because we have 3 velocities that we have to contend with: u, u prime, and v. Okay, but after we have talked about velocities, addition of velocities, we go back to the Lorentz transformation, where there's only one velocity, v. So at that point, I will drop the subscript r here. Subscript r. I will call this just v of c is just beta. If I forget to remind you this, please keep that in mind. All right? And so the next thing is to rewrite this. Okay, good. I have space here. I have space here. So let me erase this. Let me take a look at the red set of Lorentz transformation equations. And notice that x, y, z have dimension of length. So time is dimension of time. So let me in fact make this also to have dimension of length. That's easy. If I multiply by c, may I do that? C. So that's c. So that I know times c, so divide this by c. So take one out, and let me put this. C right underneath V. All right, and then, okay, I can rewrite this as one form of this is that delta x is equal to delta x prime divided by this, so that's gamma. Gamma of delta x prime plus, okay, this is also here, okay, times, okay, delta t prime by c at the same time, divide out this c by c. So that, okay, this v over c is nothing but beta, it's beta r, but I'm going to drop, okay, subscribe r, shortly, and then times, okay, c delta t prime. And, okay, this c delta t would be equal to, this is nothing but gamma of c delta t prime. Okay. Then plus this is beta sub r times delta x prime. I don't have to copy these two down because y and z components comes for right. This one form. Okay. I can also rewrite this in another form in terms of now, since I've introduced, okay, let me rewrite this. Oh, well, maybe in another form. Delta x is equal to, okay, 1 over gamma. Okay, so it's this. And this, you remember, is, what's that? What did I do? Oh, yeah. Let me write it down first. Okay. Then I explain. Okay. This can be written down as, okay, gamma, okay, delta x prime plus, okay, beta gamma. Well, in fact, it's here already. Let me copy it down. Delta c delta t is equal to gamma c delta prime. Let me put parentheses around c and delta t plus, okay, gamma, beta gamma. Doesn't matter, I'll write it, but to be consistent, but upstairs, let me put it. Plus beta gamma, okay, delta x prime. Okay, I'm going to rewrite this in terms of the hyperbolic functions. And let's see, what is, okay, gamma? Gamma is, okay, this 1 over square root of 1 minus, okay, beta r squared, beta sub r squared. And beta sub r is hyperbolic, okay, function, okay, of theta r. So minus square of tangent theta r. But that is equal to where? Oh, but that, okay, is nothing but cos of theta r, of theta. I call theta r. So 1 over square root of 1 minus tangent. So this is nothing but cos of theta r. And okay, so this what gamma is. If I multiply by here I have gamma beta r. Gamma beta r. This of course is cos theta r. Times beta r is tangent theta r. So this is nothing but hyperbolic function, hyperbolic sine function of cos times tangent is sinh, is that. So that I can now rewrite this set of Lorentz transmission expressions as delta x equals to gamma is called this. So it is delta x prime. Actually, allow me to write down the second equation first. So C delta t is equal to gamma. Gamma is this. So it's equal to cos theta r times C delta t prime. Beta gamma, I've dropped the r already. So it's nothing but sinh theta r times, run out of space again. This is gamma. Beta gamma is this, sinh, and then times, I'm writing this one. Delta x prime. And then delta x is equal to gamma is cos. And let me in fact write on the second term. But cos is the second term. The first term, then we write it here. Gamma is cos theta r times delta x prime. And then this is my sinh of theta r of this C delta t prime. And now, as I said, let me drop the subscript r. May I? From now on, drop the subscript r. So that I have. Let me just do it. Erase it. The subscript r. And the definition is this. Gamma is given by this, and this is that. And beta is defined to be this V over C. Drop into the subscript r. Of course, as I said, the y coordinates come and z coordinates come from right. So delta y is delta y prime, delta z is delta z prime. So that the Lorentz transmission, this set of equations, can be rewritten as this. Let me make one remark first. Forget about the y and z coordinates. Take a look at the time and x coordinate. The transmission rules are such that those terms on the right side involve cos, hyperbolic cosine function, and sinh, hyperbolic sine function. If I just concentrate on the time and x coordinate, then you can take a look at this equation, and you may find some similarity between the the following. Namely that if I have two coordinates, this coordinate, call this the x prime coordinate, this t prime, some kind t prime stands as there's a factor of c here. And this the x t coordinates. If you have two coordinate systems, the prime system and the unprime system, and that they are related by rotation, called theta. Then you'll notice that the transformation rules for the unprimed coordinates and the prime coordinates obey equations very similar looking to this, except that instead of cos, since you have cosine sine, actually the two can be put into each other. If you put this, say r here, call this r here, put theta r to be I theta, to be imaginary. And but at the same time, I think I t is equal c delta t. Then you can get from the two equations relating the coordinates in the unprime and prime coordinates and this two-dimensional plane to be this. So this set of transformation is some kind of rotations. But rotations involving imaginary angles and imaginary time coordinate. That's it. So it's some sort of rotations. All right, that's well, it's an interesting feature, but not crucial. And let me now go on to talk about things much more important. And I think I'm done with the identity equations, all these equations. So may I now erase all this? Because I need the blackboard space. Now, you recall that if due to a rotation in a two-dimensional plane, the rotation will not change the magnitude of a vector. And let me ask something. Oh, what happened? Oh boy. Oh, this is very upsetting. Automatically erases this sliding door. So let me recap. Okay. So this is C. Delta T is equal to what's this? Cos plus sinh theta of delta x prime delta x prime cos of theta is sinh theta is c delta t prime is c delta t prime. Sorry about that. Oh, this blackboard eraser should not slide it, but I need the blackboard space, and I have to confine to this region for the camera. Well, so if I do this, it will do the stupid thing again. Okay. Okay. I can use the other one. That's okay, right? All right. So let's do the following. Okay. let's consider space-time separations of two events. By that I mean, let me talk about spatial separation in let's see, S prime frame. Let's see, I put this. The other way around. In the S frame. Minus c squared times the temporal separation in S. I'm going to compare it with, spatial separation, in S prime. With a crucial sign minus c squared, temporal. Time, let me just call it time separation. And let me just call this space separation. Not space is space. And space separation. Time separation of those two events. Time separation in S prime squared. I'm going to compare these two. And let me start with this. In S frame, this is equal to delta x squared delta x squared plus delta y squared plus delta z squared. That would be spatial separation, square separation of the two events under consideration in S frame scale on this one. Minus is c squared delta t squared. So c delta t squared. All right? What's that equal to? Delta x is given by this. So that I have, let me copy it down. Sinh theta times c delta t y square. I'm sorry, I haven't finished. That's why I put a bracket here. What am I doing? Plus cos theta delta x prime square minus c delta t is this one, right? And this is a bracket. Oh, sorry. Oh yeah, I've already. Okay, this is square bracket. Minus this is the square of cos theta c delta t prime plus sinh theta delta x prime whole thing squared. Okay? Then, this comes for a ride. But in fact, I can, since I've expressed things into the prime here, so let me write this. Delta y is delta y prime. Delta z is delta z prime plus delta y prime squared plus delta z prime squared. Let me concentrate on this here. Let's see. Sorry. That's correct. Yeah, it's minus delta. All right? So let me take a look at delta x prime square. There is this, okay, cos theta square, and then there is this, okay, sinh with the minus sign, minus sinh square theta. Correct? All right. And then for the, okay, for this ct square, let me write this as, okay, minus c delta t prime square. I have cos again. Okay, I have cos square minus, okay, this is sinh square. So taking care of the direct terms. Now, okay, the cross terms. Cross terms involve, okay, plus delta x prime times c delta t prime. Okay, and I have, okay, this, I have, okay, 2 cos theta times sinh theta, coming from this, and then minus, okay, cross term, okay, this 2, lo and behold, cos, okay, theta, sinh theta. So that, okay, the cross terms involving, okay, delta x prime and delta t prime cancels. And then, okay, notice that I have this combination, okay, cos square minus sin square, and I've erased. You remember, okay, this is 1. This is 1. And then, of course, plus, okay, delta y prime square plus delta z prime square comes from these two. So that, okay, the left shows that, okay, this is equal to, okay, delta x prime square minus, okay, c delta t prime square and plus delta y prime square plus delta z prime square. Okay. So this is, okay, space separation in S frame minus square of time separation in S frame. And that now has been shown to be equal to space separation in, okay, S prime frame minus c squared times time separation in S prime frame. So they're equal. So even though space separation in one frame is not equal to space separation in another frame, and time separation in one frame is not equal to, okay, time separation in another frame, but the combination of these two, space separation square minus time separation square, is invariant under Lorentz transformation. Okay, that is in space-time separation given by this, okay, is equal to space-time separation. Space-time separation in S frame is equal to space-time separation in S prime frame. So that, okay, space-time separation. The square is given this. So let me just say that space-time separation is invariant under Lorentz transformation. By space-time separation, I mean this. Okay, this combination of square of space separation and, okay, square of time separation in that manner. Okay, so it's a nice thing to know. There's certain kind of things, intervals, being invariant. And let me, I need a paper space here. Let me just do it. Sometimes this combination of space separation and time separation, notice that that's the minus sign, is known as the interval of space. What I have to be careful. Okay, interval, this combination is sometimes called interval of proper distance squared. And sometimes it's also this is also known as well. Let me put out this c squared minus c squared of the square of interval of proper time. That's certain terminology. And this terminology is not important. Whereas in the literature, you would encounter this second one, namely things which people call proper time. And now let me, in fact, go on to talk about this, something important about this proper time. And yes, I can use this blackboard, and there's no, and that's okay. All right. So what's next? And I would like to leave, I have to be careful, not to erase things that I will need in a moment. Oh. Have I erased it? Okay, well, all right. I think we know. So I want to keep this safe. All right. So I have to make use of this blackboard. Oh, I can do it here. Okay, let's say a few words. Let's say a few words to explain the physical significance, physical meaning of proper time. So let me make use of the fact that this invariance under Lorentz transmission, this measure of space-time separation. And so let me consider a certain system. So this is the S frame, this is the S prime frame. And this prime frame is always understood to move relative to S frame with velocity to the right towards positive x-axis. And let's say that the system is moving in S frame with velocity v. So that in S prime frame, that system is at rest. So that for this system, moving velocity v, so let me make use of this. So that we know that this is true. Space separation in S frame. Let me consider those two events that we're interested in. In fact, are very close to each other. So let me teach notation: capital delta to d differential quantity. So that we have, all right. What is so this combination of space separation and time separation is invariant. And let me write the invariant quantity as ds squared when the delta becomes d. Okay. This is invariant. And it's given by spatial separation, okay, which is okay, dr squared minus c okay, dt squared. Okay. And it's supposed to be equal to, since it's invariant, it's equal to dr prime squared minus c dt prime squared. Because we have shown that okay, this combination of space separation and time separation been invariant, okay, under Lorentz transformation. So this quantity, as measured in the S frame, should be equal to this quantity, same quantity measured in another frame, the S prime frame. Okay. Okay. So let me write this down. dr. So in an infinitesimally small dt amount of time, okay, this system will have moved a distance dr, okay, which is given by v dt. And since I'm always talking about just the x, okay, so in fact I can, so that the invariant quantity, invariant space-time separation, which we now call ds squared. This s is not to be confused with okay, s stands for S frame, but okay, people like to call this combination of okay, space separation square minus okay, time separation square, denoted by ds squared. And this okay, combination is invariant, and ds squared is invariant under Lorentz transformation. All right, so this is okay, given a dr squared, which is v squared, okay, times okay, dt squared. Square of dt. Minus c times the c squared. So if I okay, pull out my signs of minus, and let me put okay, c squared. Then there's 1 minus okay, v squared over c squared. V over c is my beta. So 1 minus beta squared. Times dt squared. On the other hand, this invariant quantity is that in the okay, given by this in the okay, S prime frame. So ds squared is equal to this. Well, okay, this okay, system is at rest. So in the infinitesimally small okay, amount of time, t prime, okay, dr is 0. So 0 minus c dt prime squared. All right, and okay, this system is at rest in this system, and it's customary to write the time coordinates okay, as denoted by tau. I'm sorry. Yeah, right. That's okay. So tau is the time as measured. Why am I having a problem with this? So tau is the time as measured in the rest frame. Okay. So tau has the significance of okay, time as seen in the rest frame of the system under consideration. Let me write in the rest frame of the okay, of the system. That's the meaning of okay, tau And this tau is, since it is given by only this term, time term, so that is to be compared with the space-time separations given by, in terms of the so-called square of interval of proper time, that's minus c squared, is equal to this minus c squared, so that this tau is the proper time of the system. It is time as seen in the rest frame of the system under consideration. All right, so what's that in terms of the quantities in the unprime frame? All right, since ds squared is equal to this ds squared, so that I see that this ds squared is equal to minus c squared. T prime we call it delta tau, so delta tau squared. And do I want to incorporate? Yeah, let me use the. So that I have d tau square. If I can take out now minus c square is equal to 1 minus beta square times the square of dt squared. If I take the square root, that means the d tau is equal to square root of 1 minus beta square dt. So square root of 1 minus beta square is nothing but 1, the reciprocal of gamma. This is 1 over gamma. So that d tau, tau being the proper time, is equal to dt over gamma. And you will have to make use of this when we go on to talk about relativistic mechanics. Shortly, we'll do that in the 2 lectures from today's lecture. In relativistic mechanics. All right. Now, it turns out that in fact I've spent a lot more time on the math than I intended. And now let me go back to this equation. And I can erase all this now. I can erase this. Let me talk about this. Let me multiply both side by c so that I have ct, I will have the same dimension as the coordinate. So this c cancels along this c. And multiply this by c, then divide this by c. So that I can rewrite this as ct prime is equal to ct minus v over c. Of course, it's just beta x. And this is nothing but gamma. So it's gamma outside. And this one is x prime is equal to, gamma of x minus beta ct. Then y is equal to this. I'm sorry, it turns out that I'm running slow. I can't catch it.
Oh, okay.
Yeah, it will be 10 minutes or so. Thank you. It's equal to Z. All right. And since I'm running slow, let me quickly do this. Yes. Okay. All right. At this point, okay, it is a useful thing to do to introduce some new notations. Define. Okay. You notice that time and space transform among themselves. So it's natural to combine the three coordinates, spatial coordinates, with time being the fourth coordinate. Actually, in the literature, the time is regarded as not the fourth dimension, but the zeroth dimension. So let me introduce what's the contravariant. I'm not going to contravariant. Vector. The space vector. So it's denoted by x. Okay, make use of the fact that we are talking about just one of the coordinates is x. X mu, and mu runs over 0, 1, 2, 3. And this defined to be, notice that mu appears in the contravariant vector as a superscript. And the zeroth component is written down first, and that is CT. And then, the x1 is x, x2 is y, xz, x3 is z. And then let's introduce also the covariant vector. They got to do with space, time, coordinates. Covariant vector is for this space-time, coordinate, and time, is denoted by x subscript mu. Mu also takes value 0, 1, 2, 3. And the first component, or the zeroth component, is minus CT. The other components the same as before, x, y, z. So that the contravariant vector and the covariant vector only differ for the zeroth component by sign. And we have to introduce both that differ by sign because of the fact that in space-time intervals, there's this minus sign. There's minus sign distinguishing the time component and the space-time component. Now, we can, it's here. Well, now we can, rewrite this. Well, we can write, let's see. So that, let's make a Lorentz transformation. Lorentz transformation. So that I take, under which x mu go into x prime mu. And, now with this set of equations, we can write down how x mu prime is gotten from x mu. And let me write this as x prime mu is given by lambda mu x mu, when mu also runs over 0, 1, 2, 3. And repeating this mu here implies summation. So you're using the Einstein summation convention. So sum of the four terms with say mu 0 being 0, then 1, 2, 3. Then you can rid off, from this equation, to be lambda mu nu is the so-called Lorentz matrix, Lorentz transmission matrix. Is given by the first row refer to 0, first column refer to 0, etc. So that you will have the y and z component. It's just there for a right. Let me write this. It's a can be written as a 4x4 matrix. I may not have enough space. So that along diagonal, here 1, 1. So that tells me that y is y prime. And here, you have, in terms of the gammas, you have here gamma, gamma, minus gamma, beta, minus gamma, beta, and the others in 0. I thought that this is going to be a very short lecture. It turns out that, in fact, because of the fact that I made some mistakes in calculations, and because I took the time to do some trivial calculations, so in fact, this lecture is not that short after all. Okay, you can check that this Lorentz transmission given with this Lorentz transmission matrix given with this will be produced this result. And you remember that we also introduce the Cauchy and Singe. Let me in fact also invite you to Shane just came to me, so I have to stop very soon. So let me in fact leave it as an exercise, a simple exercise, but things are now given all over the blackboard, so I'm confused. So let me not embarrass myself doing the algebra. But it's also equal to, given by a 4x4 matrix. 1, 1, and all this 0, 0. And the important things will be in the 2x2 matrix here. And this is, in terms of gamma beta, is of this form. In terms of the hyperbolic function, is cos beta minus sinh beta minus sinh beta cos beta. There will be. And okay, next one last thing. Then Shane is coming. Then I have to stop. Okay, so now. So we've introduced two kinds of vectors, contravariant vector and covariant vectors. And how can we transform one to the other one? To do that, we have to introduce a metric. So introduce metric to do it. And let's introduce metric called G mu nu. Both is a tensor, metric tensor. It carries two indices. And G upper mu is defined to be almost like the identity matrix. Except for the fact that the left upper element is minus instead of plus. 1, 1, 1, 1. The others been 0. And this minus 1 here, it will be used to change, from plus CT in the contravariant vector to minus CT in the covariant vector. And this is also given as G subscript mu subscript nu. So in terms of this metric, G mu nu, then I can do the following. I'm done, so I can erase everything, in fact. So that I can write X superscript mu the contravariant vector in terms of the covariant vector multiplied by the metric tensor G mu nu. Okay, the summation indices always one appears as subscript, the other one superscript. And I can also obtain the covariant vector from the contravariant vector by applying this G lower mu nu. By the way, G lower mu nu is same as G upper mu nu. So this G mu nu. That's how you relate the two kinds of vectors. And I think I should stop here. And so this is the point where we'll pick up in the next lecture, which, by the way, was already recorded, taped. So it's a good thing that I could end at the point where which will serve as the starting point for the next lecture, which already was taped. So I knew before coming here today that I have to stop here so as to connect it with the starting point of the next lecture.